It's been a while, and here's your first video for 2021. It's in your ISN, probably page 72. You have to cut the sheet into 3 equal pieces, and then you fold it so you can see the words simplify, multiply, divide, rationalize, add and subtract, and then a staple at the top if you haven't already made your foldable. So what are radicals? Because we haven't used this word yet, but you know what they are. It's actually the one we've seen all the time is the square root. That is a radical sign. Sometimes, and we've seen this, we'll take the cube root of something. If we've multiplied something 3 times, right? We'll take the cube root of it and we will get 3. The square root, when we did something like 25, that awesome perfect square that really multiplied 5 times 5, when we take the square root of that, we know it was 5. So radical signs are like square roots and cubed roots. They're called a radical sign. This indicates what root you're actually taking. The word is the index. So you see here we took the cube root. And then underneath the radical sign, it's just called the radicand. All right, so get your foldable together and get started with radicals. And I am going to go over the notes. So the very first one, when we are looking at these radicals, what I want you to look for is the perfect square. So you should have a box above these two examples. And really what you want to say is you want to look for perfect squares when you're looking under square root signs, or perfect cubes when you're looking under cube root signs. Perfect squares are ones that when I take the square root of them, I actually get a whole number. Okay, so the square root of 1 is a perfect square. The square root of 4 is a perfect square. That root is 2. The square root of 9 is a perfect square. 25, you have a list of them in the front of your ISNs, and you start to recognize these perfect squares. That's what you're looking for when you have a square root. When you're looking for cubed roots, you're looking for perfect cubes, right? So the cube root of 1, when you think about it, it is going to be 1. The cubed root of 8. What did I multiply 3 times together? So the cubed root of 8, well, 2 cubed, 2 times 2 times 2 is 8. 2 cubed. If you take the cubed root of it, it's 2. Look at those things canceling each other out, right? The cubed root of 27, think about this one, right? 3 times 3 times 3 are the factors, 9 times 3, so 3 cubed is 27, and the cubed root of that is 3. Okay, so you got to look for these perfect squares when you're looking at rational numbers. If it says to simplify. When I look at 32, I see that a perfect square is 16, and I would multiply that by 2 because 16 is 4 squared times 2. And I know that the square root of 4 squared times the root of 2 is 4, so it can be written as 4 root 2. Okay, we've done these at the beginning of the year. Again, you are looking for perfect squares. When I see 75, you should recognize it's going to be 25 times 3 are the factors of 75. X squared times x, now that we've been doing exponents, that's x cubed. Well, 25 and x squared are perfect squares. Okay, so I'm left with the root of 3 and x. Okay, I've just rearranged those. Remember, that's the commutative property. And I know the square root of 25 is 5. The square root of x squared is x. And I'm still multiplying it by 3 root x. All right, so take those notes down into your ISN, and hopefully we'll practice those more when we go to school. Page 2. The product property. We kind of already did this. We already saw that the square root of a is b is the same as the square root of a times the square root of b. Okay, so if I take the square root of each of those numbers and multiply them, I will get the same thing. Let's look at an example. If I multiplied these under the square root, I would have 9 times 9. That would be the square root of 81. or the square root of 81 is 9. For now, we're just going to deal with the positive answer. If I took the root of these, I would get 3. The square root of 3 is 9 times the square root of 3 is, or the square root of 9 is 3, and the answer is 9. So either way, you get your answer is going to be 9. Because when you multiply underneath the square root, it is going to be the same thing as taking the square root and multiplying. Okay, so the next equation that they did for you, that they simplify, or they want you to simplify, is these are all under the square root. So 3 can be multiplied by g times 2g cubed. That's a g. Okay? Because they're both under the square root, they're both to the power of root 2, square root of 2, we can put those under the square root. So then we could rewrite this as root 3 times 2g to the 4th. Okay. Oh, but maybe, hopefully, you recognize you could take the square root of g to the 4th. So you actually have 3 times the square root of 2 times the square. Oh, I lost the thing. Let me rewrite it. 3 times the root of 2 times the square root of g to the 4th. Well, g squared times g squared is g to the 4th. So you could actually write it as 3. I'm just rearranging, right? G squared times the root of 2. This guy can be simplified when you're looking for perfect squares. You will get 3g squared times the root of 2. Okay? If it is under a square root, you can put it all beneath the square root. So you can have 2 times the square root of n squared times 5m squared. I am going to get you to try and simplify that one and see what you get when we get back to school. So multiply those and simplify. Okay. When we divide, the quotient. Okay, the quotient of something is the same as taking the root of A and dividing it by root B. We have seen these ones before. So what does that mean? That means that 5 over 49 is the same as taking the root of 5 and dividing it by the root of 49. Well, the root of 5 is an irrational number. You get some crazy decimals, so we just leave that. But the root of 49, I know what that is. It's 7. So I could rewrite this as 5 root 7. The next example, when I have 11 over the root of d, it is the same as taking the square root of 11 and dividing it by the square root of d to the power of 4. We need to think about perfect squares, so that means whatever I multiplied by, if there's something I multiplied by itself to get there, it is a perfect square. Well, the root of 11 is an irrational number. It has no factors that are perfect squares, but the root of d to the 4th, d squared times d squared gives you d to the 4th. That is the same number, right? So when I can actually take the square root of that, and I'm going to get the root of 11 over d squared. Okay, get these in your notes, and we will do more practice when we get to school. All right, the next page, you might need to pause to get these in your notes. Rationalizing a denominator. We have not heard this word before, but the whole idea of rationalizing the denominator means you cannot leave a square root in the denominator. So you need to get rid of the square root, in the denominator. Okay. All right. And how we need to think about this. We need to remember that any number divided by itself is equal to 1. So if I'm multiplying the top and the bottom by the same number, it doesn't change anything. So I can get rid of a square root of 5, for example, if I multiply it by a root of 5. Okay, what I mean by that is 5 times 5 is 25, and the square root of 25 is 5. Okay, so those are the two things I am thinking about when I rationalize a denominator. When I multiply the top and the bottom by the same thing, it's like multiplying by 1. And to get rid of a square root sign, I need to multiply it by the same square root. So I have the square root of 6 on the bottom, and I can't leave a root on the bottom. So I am going to multiply it by the square root of 6. That'll get rid of it. But if I do that to the bottom, I have to do it to the top. This is like multiplying by 1, so it's not actually changing anything. It leaves you with 7 times the square root of 6, but the square root of 6 times the square root of 6 is the square root of 36. Oh, wait, that's now a perfect square, so I can simplify it to just 6. So to rationalize, we're getting rid of the square root sign in the denominator. Basically, you're looking at the square root sign in the denominator, and you're multiplying the top and the bottom by the same thing. So that will get rid of the root, because I will have on the bottom the square root. If they're under the square roots, you just multiply 25a squared. And in the top, when I multiply those, I will have 3 times 5 is 15, and I have 1a left over there. But this is a perfect square. So I'm going to rewrite this as 15a over 5a. Okay, so I've multiplied the top and the bottom by the same thing. Rationalize means to get rid of the square root in the denominator. Okay, the last examples, we've done these before, and we need to think of this as a number, an x, okay? So when I am adding and subtracting, I need to add and subtract like terms. There are no perfect squares under these, but I have 7 roots of 14, and I am subtracting 14 roots, or 4 roots of 14. So because this is the same number, you can think about it like it's an x. Okay, and I can add like terms. 3 root 14 minus 4 root 14 is going to, oh my goodness. You know, I wrote, okay, I'm not redoing this because I'm too close to the end. 7 minus 4 root 14 is 3 root 14 plus the square root of 21. This is the same number, so I can tell you I had 7 of them. I took away 4. Now I have 3 root 14. Okay, it doesn't look like there's any same numbers here, but wait a minute. I know a perfect square in 28. 5 root 7 plus 28 is 4 times the square root of 7. The 4 is a perfect square. So I actually have 5 root 7. I take the square root of 4, and I have 2 root 7, which means I have 7 root 7s. Write these examples down in your notes, and we will look at them more tomorrow. The second video is going to be ISN page 73, rational exponents.